In section 3.6, we're going to talk about the chain rule. So in previous sections, we discussed techniques for differentiating our basic functions like x to the n, sine of x, cosine of x, tangent, all of the trig functions, etc. We've also learned rules for differentiating sums, differences, products, quotients, and constant multiples of those same functions. But what happens when we have composite functions? For instance, how do we differentiate functions like sine of x cubed? Or g of x is equal to the square root of 3x squared plus 1. For this, we need another approach. We need a way to figure out how we're going to differentiate composite functions. And that's where the chain rule comes in. So if we have f and g, and they are continuous functions, we can say for all x in the domain of g, for which g is differentiable at x, and x is differentiable at g of x, the derivatives of the composite function h of x equals f of g of x is given by h prime of x, which equals f prime of g of x times g prime of x. Another way to think about it is if we're looking at dy dx, we can look at dy du times du dx. If y is given in terms of u, and u is given in terms of x. So when we go through some of our derivatives, we may employ a technique called u substitution, where we're going to let part of our function that's in terms of x, we might define it as u, and let u of x be that part of the function, and then employ our chain rule in this manner. It will also be a really great introduction on how u substitution will work when we look at integration, which is an antiderivative, and it's something that you'll find extremely useful, especially in Calc 2. So the most obvious rule for our chain rule is when we mix it with the power rule. So for example, if we have a function h of x that is equal to another function g of x that's raised to a power of r, then its derivative will be r times g of x to the r minus 1. There's the power rule part, times the derivative of g of x. There's the chain rule part. All of this is because every piece of our function contributes to the slope of our tangent line. If we didn't multiply by g prime of x, we would be missing a component to the true value of that derivative, that slope of that tangent line. And that is truly at the heart of why the chain rule works the way it does. For our first two examples, we're going to start out doing everything the long way, and I'm going to give you the two hardest examples from the section first. So where we're starting is we're going to find the second derivative of each of these functions. We begin with a. A says h of x is equal to 1 over 3x squared plus 1 quantity squared, which I'm going to tell you to rewrite and bring the 3x squared plus 1 to the numerator, so it becomes to the minus 2 power. Reason being, now when we apply our chain rule, this is going to be a lot simpler. Bring down the negative 2, multiply by 3x squared plus 1. Now take 1 away from the power, so negative 3, and then we'll multiply by the derivative of 3x squared plus 1. So we end up with negative 2 times 3x squared plus 1 to the negative 3 times our derivative of 3x squared plus 1, which is just 6x. So we end up with negative 12x times 3x squared plus 1 to the negative 3. Not terrible, right? That's not a bad first derivative. The thing is, I asked you to find the second derivative. So when we find the second derivative now, we have to think of this more as a product of functions. So now we have to use the product rule to find our second derivative. So h double prime of x here, let's scoot it up a little here so we can see it a little bit better. H double prime of x now is going to be the first, so negative 12x times the derivative of the second, and that's going to be our 3x squared plus 1 to the negative 3, plus our second, 3x squared plus 1 to the negative 3, times the derivative of our first, which is a negative 12x. So we end up with negative 12x times, well, our derivative now for 3x squared plus 1 to the minus 3 is going to look very similar to what our derivative looked like for 3x squared plus 1 to the minus 2. We're going to bring down the negative 3, and then we have 3x squared plus 1 now to the negative 4 times the derivative of 3x squared plus 1. So what happens is we used the chain rule up here in our first derivative to find our solution. Well, now we're using the product rule, and within this product rule, we're also using the chain rule. So this derivative requires the chain rule. So you can see quickly how we're going to end up putting together product rule, quotient rule, power rule, and the chain rule all together for pretty much every function that would come up in real life. So let's finish out this derivative. We end up with our 3x squared plus 1 to the minus 3. Now our derivative of negative 12x is just negative 12. So we can see already that we're going to be able to pull out a negative 12, but we'll get to that later. So let's see what we've got left then. We've got, let's see here. Well, negative 12x times negative 3 gives me a positive 36x. I have my 3x squared plus 1 to the minus 4. And our derivative of 3x squared plus 1 is 6x. Then we've got minus 12 times 3x squared plus 1 to the minus 3. And this is where the fun happens because now we have to factor out what's common. And both terms have a 12, and both terms have 3x squared plus 1. But the catch is to take out the highest number of these 3x squared plus 1s. So for us, that means that when we look at two expressions that have the same factor in common and they both have a power, we take out the lower power. So here, negative 4 is lower than negative 3. So we're going to take out 3x squared plus 1 to the negative 4. What that means then is we have taken out all of these 3x squared plus 1s to the 4. Right? We now are going to end up having 1 left here because negative 4 plus 1 will give us a negative 3, so we will have one of those left. And we took out a 12 here, and we took out a 12 here. So we end up with 3 and an x. And then don't forget that 6x that was left at the end. And then we have minus just a 3x squared plus 1 to the 1. And remember, that is because negative 4 plus 1 equals negative 3. So now that we have factored out our 12 and our 3x squared plus 1 to the negative 4, we can simplify the leftovers here, as we'll call them. What's left after we factor, we've got 18x squared minus 3x squared and minus 1. So we end up with 12 times 3x squared plus 1 to the minus 4 times 15x squared minus 1. And that is our solution for our second derivative. It's a lot of work, but if you just stay the course with the rules and with the algebra, you will get there. Let's try B. B says that I've got f of x equals sine of x times cosine of x plus x over cotangent of x. So this was the problem we didn't get to on the end of section 3.5, which is okay because we could have found the first derivative, but the second derivative we could not have done without the chain rule. So let's see if we can figure it out now. Let's start with f prime of x. Well, we have a product rule, so sine of x, right, times cosine of x. So sine times the derivative of cosine plus cosine times the derivative of sine. So we'll start with that part. And then we have a quotient rule. So you can either leave it as a quotient, which is what I'm going to do, or you can say that 1 over cotangent is tangent, and you can make it an x tangent x and do another product rule. Completely up to you. I'm going to solve this one as if it were a quotient. So we would have low, which is cotangent x, times the derivative of the top, which is x, minus the top x times the derivative of the bottom, which is cotangent x, all over the bottom cotangent of x squared, so cotangent squared. So let's simplify some of these derivatives. We end up with sine x times negative sine x plus cosine x times cosine x plus, now we have cotangent x times, well, 1, right? Minus x times the derivative of cotangent is negative cosecant squared x. And this is over cotangent squared x. So we end up with a negative sine squared x plus a cosine squared x. Unfortunately, that means we can't use our Pythagorean theorem, here our Pythagorean identity, and make this 1 because it's a negative and not a positive. So we'll keep it as sine squared x, or negative sine squared x plus cosine squared x. Then we'll add our cotangent x. Now it's going to be plus x cosecant squared because of the two negatives multiplying. X cosecant squared x all over cotangent squared x. And this is where we can simplify our lives quite a bit because we can say that this is the same as sine squared or negative sine squared x plus cosine squared x, right? Plus, now turn all of the cotangents and cosecants into sines and cosines. So cotangent would be cosine x over sine x plus x, and cosecant is 1 over sine x, so that'd be sine squared x. And it's divided by cotangent squared, so it'd be cosecant squared x over, or sorry, cosine squared x over sine squared x. So if we do that, we can simplify this to negative sine squared x plus cosine squared x plus, now this would be cosine x times sine x plus x over sine squared x times sine squared x over cosine squared x. And what that means then is that our sine squareds are going to cancel, and we're going to end up with negative sine squared x plus cosine squared x plus, well, 1 over cosine squared is going to be secant squared, so I'm going to move that to the front, or secant squared x times cosine x sine x plus x. So that was a lot of moving around our trig, but that certainly made this first derivative a lot easier to handle now for us to take the second one. We don't have to do another quotient rule. So remember how I said just check to see if simplifying will make your life easier. In this case, it definitely will make it easier. We're still going to have to use the product rule. We're still going to have to use the chain rule. But at least we also don't have to use the quotient rule in addition to both of those. So now let's find our second derivative. So now f double prime of x, let's see here, we'll scoot it up just a little here. Let's see here, so f double prime of x will be, then now we have negative sine squared x. So it would be negative, and we'll bring the 2 down. It is still sine of x then to the 1 times the derivative of sine x. That's our chain rule, right? Plus cosine squared of x is going to be 2 cosine of x now to the 1 times the derivative of cosine x. And this is where the interesting part is going to happen because now we have a product rule mixed with the chain rule. So we're going to do the first, which is secant squared, times the derivative of the second, which is cosine x sine x plus x. And you see within that, we're going to have a product rule. Plus the second, cosine x sine x plus x, times the derivative of the first. So let's see if we can fit it in there. Times the derivative of secant squared. There, I think we fit it. So we end up with negative 2 sine x times cosine x plus 2 cosine x times negative sine x plus secant squared x times. And now we've got cosine x sine x plus x. Well, let's see what happens when we do cosine x sine x, which, by the way, we've already done. We would get cosine x times the derivative of sine x is cosine x plus sine x times the derivative of cosine x, which is negative sine x, plus the derivative of x, which is 1. That is the first times the derivative of the second, and then we will add, I'll have to add it underneath, I kind of ran out of space, the second, which is cosine x sine x plus x, times the derivative of secant squared x. This is where our chain rule is going to come in. It would be 2 times secant x, now to the 1, times the derivative of secant x. So we end up with negative 2 sine x cosine x, okay, sine x cosine x, there we go, minus another 2 cosine x sine x, it's the same thing, plus, well, something interesting happens. Let's see here, secant squared x times cosine squared x minus sine squared x plus 1 plus 2 secant x, just moving a few things around here, 2 secant x, and the derivative of secant is secant x tangent x. And then we still have our cosine x sine x plus x. So now we end up with a total of negative 4 sine x cosine x terms plus a secant squared x times cosine squared x minus sine squared x plus 1 plus 2 secant squared x's tangent x times cosine x sine x plus x. Ooh, it's a lot. But what we can do is we can leave it here, or we can factor out a secant squared from the last two terms. It's really not going to help us get anywhere, because if we did that, we would have cosine squared x minus sine squared x plus 1, and we'd have 2 tangent x times cosine x sine x plus x. So it's not going to really get us anywhere, so we're going to leave it at this step, which I'm sure is not going to be terribly disappointing to any of you, because that was a lot of work. For the next page, we're going to lean into that second explanation for the chain rule, that second definition for at least the first 3 problems on this page. We could use it for more than 3, but it's going to be easiest on the first 3. How this works is we will start with letting u equal the part of our function that is in terms of x. So here it will be u equals 3x squared, and then we will find du dx. The derivative of u with respect to x, well, here that would be 3 times 2 is 6, x to the 2 minus 1 is just 1, so it would be du dx is 6x. Then we would say p in terms of u then would be cosine of u, and we look at dp du. So the derivative with respect to u of cosine of u is negative sine of u. And then the derivative we're looking for is dp dx. And the way we're going to find dp dx is we're going to say dp du times du dx. And in a rudimentary way, we can look at it as two fractions where the du's cancel out and we're left with dp dx. It's a little more complicated than that, but that's probably the easiest way to remember it. So dp du is negative sine u, and du dx is 6x. Notice that we still have a u in here, so it can't truly be dp dx when we still have a u. So the way we'll finish it out is say negative 6x times the sine of u, and we let u back here be 3x squared. So we'll make it back to 3x squared. And that comes back. All right, and that's how we finished this one. That's it. That is the entire derivative. Do you have to do it with u's? You do not. You could say that it is the cosine of 3x squared times the derivative of 3x squared. So the derivative of cosine of 3x squared times the derivative of 3x squared will also work. It's just a little easier to see when we put it in terms of u substitution. So we're going to try another one. For q, we're going to let u equal 5x to the fourth minus 3x. So du dx is 20x cubed minus 3. That makes p, in terms of u, be secant of u. And dp du then would be the derivative of secant is secant tangent. So it would be secant u tangent u. And now when we want to find, oh, I did p's. Sorry, those should all be q's. The p's should, both of those p's, sorry, should be q's. I was stuck with the last problem. There we go. So they should be dq du, and q should be secant of u. So when we look for our derivative dq dx, we will get dq du times du dx. Or dq du is secant u tangent u times du dx is 20x cubed minus 3. Now the last step we need to do is to just substitute in what u is. So secant of 5x to the fourth minus 3x, tangent of 5x to the fourth minus 3x, all times 20x cubed minus 3. And there is our derivative. We're going to do one last example using this u substitution, and then we're going to move into more chain rule with product rule for the last two on this page. So let's look at C. C says I've got 8x cubed minus 5x squared plus 2x plus 3 all to the minus 2. I want you to let u equal 8x cubed minus 5x squared plus 2x minus 3. Du dx then would be 24x squared minus 10x and plus 2. So now we have f in terms of u. So f is now u to the negative 2. And df du would be negative 2 u to the negative 3. And now when we want to find df dx, it's going to be df du times du dx. And df du is negative 2 u to the negative 3. Du dx is 24x squared minus 10x plus 2. So we end up with negative 2. U is now 8x cubed minus 5x squared plus 2x minus 3 all to the negative 3 times our 24x squared minus 10x plus 2. I ran out of space over there, sorry. We're not going to be able to do the same u substitution necessarily for the last two. It will require a little bit more work. We could let u be 2x minus 1 and v be sine x minus cotangent x, but it doesn't really get us a lot of places very easily. It doesn't really help simplify anything because here we have two functions that are multiplied together that have to be treated as such when we take our derivative. So here we'll have h prime of x is first, so 2x minus 1 cubed, times the derivative of the second, which is sine x minus cotangent x, plus the second sine x minus cotangent x, times the derivative of the first, which is 2x minus 1 quantity cubed. So we end up with 2x minus 1 quantity cubed, and our derivative of sine is cosine. And our derivative of cotangent is a negative cosecant squared x. So we make it a plus cosecant squared x. Plus sine x minus cotangent x. And now our derivative using the chain rule of 2x minus 1 to the third is going to be 3 times 2x minus 1 squared times the derivative of 2x minus 1. So we end up with 2x minus 1 cubed times cosine x plus cosecant squared x plus sine x minus cotangent x. Let's see here. Sine x, there we go, minus cotangent x times 3 times 2x minus 1 squared times 2. So now we want to see what is common and what we can factor out. It looks like we can take out a 2x minus 1 squared. So we'll have a 2x minus 1 left on the first one. That appears to be all we can take out. So let's take out 2x minus 1 squared. Then on the inside, we're left with 2x minus 1 times cosine of x plus cosecant squared x plus 6 times sine x minus cotangent x. And unfortunately, that is exactly where we have to leave it. There is really nothing else here that we can do to simplify. So sometimes these problems with the trig functions are just going to be complicated. Their answers are going to look complicated. There's not always a way to tie them up with a nice little bow and make it look really pretty. If you wanted to, you could spend tons of time sitting there trying all kinds of different identities and formulas, but in the end, you might find something that could help, but realistically, you'll have spent so much more time looking for an identity that would help or a formula that would help that you could have done 12 other problems. So we're going to leave this one as it is, and we're going to try this last product on this page. And this one is a product of two binomials that have an exponent. So this one's going to be chain rule by chain rule by chain rule by chain rule by chain rule. There's going to be a lot of chain rule in this one. So let's see what happens when we start taking our derivative. B prime of x is going to be the first, so 2x plus 1 to the fifth times the derivative of the second, which is 3x minus 4 to the sixth, plus the second, 3x minus 4 to the sixth, times the derivative of the first, which is 2x plus 1 to the fifth. So 2x plus 1 to the fifth times, now bring down the power, 6. 3x minus 4 stays the same. 6 minus 1 is 5 times the derivative of 3x minus 4, the derivative of g of x here, the inside. Plus, then we get 3x minus 4 to the sixth times. Same deal. Let's bring down our power of 5. 2x plus 1, now to the 5 minus 1 is 4, times our derivative of the inside function, which is 2x plus 1. So we end up with 2x plus 1 to the fifth times 6 times 3x minus 4 to the fifth times 3 plus 3x minus 4 to the 6th times 5 times 2x plus 1 to the 4th and times 2. Ooh, that was a lot. Let's see if we can figure out something that is common to all of it, but let's maybe combine some of these numbers a little bit. 6 times 3 gives me 18, and then I've got 2x plus 1 to the 5th and 3x minus 4 also to the 5th. And then we've got, from there, we've got, let's see here, 5 times 2 is 10. And let's put them in the same order to make it easier to see what we can factor out. 2x plus 1 to the 4th times 3x minus 4 to the 6th. So now we have to figure out what we can factor out. Well, it looks like if we look at the 2x plus 1s, we've got 4 on the second-hand term, so we'll take out all but 1 on the first term. But we can take out all of the 3x minus 4s on the first term and all but 1 on the second term. And then the last thing we have is the 18 and the 10, from which we can pull a 2. So lots of things to factor out. Let's take out the 2. 2x plus 1, we said we were going to take out 4 of those. 3x minus 4, we said we were going to take out 5 of those. And let's see what's left. So from the 18, we pulled 2, so we have 9 left. We still have a single 2x plus 1. And we took out all of the 3x minus 4s to the 5. For the second term, a 10, we removed the 2, so we're left with 5. We took away all of the 2x plus 1s to the 4th, and we have 1 3x minus 4 left. So this should simplify into something really nice to look at. So we have 2 times 2x plus 1 to the 4th times 3x minus 4 to the 5th. And on the inside here, we get 18x plus 9 plus 15x and minus 20. When we do a little bit more simplifying, we end up with 18 plus 15 is 33x, and 9 minus 20 gives me negative 11. So really, we can pull an 11 out of this last factor. So we end up with 22 times 2x plus 1 to the 4th times 3x minus 4 to the 5th. And now that we took away the 11, that would be 3x minus 1. So much nicer to look at than all of the ones with all the cosines and the sines. A lot of these problems are just going to take a lot of algebra to get them finished. Continuing on the same example problem, if we look at g of x here, so this is problem part F, but it is g of x, we have x over 2x minus 3 quantity cubed. You can either use the quotient rule as it is, so we can do the quotient rule, or you can bring up the 2x minus 3 to the 3rd to a negative 3, and you can use the product rule. Either way is fine. I'm going to use the quotient rule first. So let's do g prime of x, and we'll use the quotient rule. So g prime of x here would be low, 2x minus 3 cubed, d high, so derivative of x, minus high, which is x times the derivative of the low, which is our 2x minus 3 cubed. All over low, 2x minus 3 cubed, squared. So we end up with 2x minus 3 cubed times 1 minus x times, bring down the 3, 2x minus 3 now to the 2 times the derivative of 2x minus 3. All over 2x minus 3 was cubed, and it got squared on top of that, so we would do 3 times 2 here. We have a power to a power, so we multiply. So it's now 2x minus 3, quantity to the 6th. So we end up with 2x minus 3 cubed minus, let's see here, we get 3x times 2x minus 3 squared, and then the derivative of 2x minus 3 is just 2, all over 2x minus 3 to the 6th. And if we pulled out 2x minus 3, we could take out 2 of them here, and it'll leave 1 in the first term, so we end up with 2x minus 3 quantity squared times 2x minus 3 minus 3x times 2, all over 2x minus 3 to the 6th. So notice we have 2x minus 3 squared in the numerator and 2x minus 3 to the 6th in the denominator, so we can cancel out 2 of the 2x minus 3's in the denominator. So we end up with 2x minus 3 minus 6x all over 2x minus 3 to the 4th, which we would then end up making 2x minus 6x is negative 4x minus 3 over 2x minus 3 to the 4th. So that's what this problem would look like with a quotient rule. If we wanted to do the product rule instead, we would do g of x is equal to x times 2x minus 3 to the negative 3. So g prime of x would be x times the derivative of 2x minus 3 to the negative 3rd plus 2x minus 3 to the negative 3rd times the derivative of x. Which means then that we have x times negative 3 times 2x minus 3 to the negative 4 times the derivative of 2x minus 3 plus 2x minus 3 to the negative 3 times the derivative of x is just 1. So if we simplify this a little bit, we get negative 3x times 2x minus 3 to the negative 4th times 2 plus 2x minus 3 to the negative 3rd. If we were to factor out what's common, which would be a 2x minus 3 to the negative 4th, we would take out all of these ones and all but one of those ones. So we would end up with negative 3x times 2, right, plus 2x minus 3. So what do we end up with? 2x minus 3 to the negative 4 times negative 6x plus 2x is negative 4x minus 3. We got the exact same thing. You can do it whether you use a quotient rule or the product rule here. It wouldn't bother me either way. I just wanted to show you both ways. For the next problem, we're going to go back to our u substitution and make our lives a little bit easier on this one, because here we have cosine to the 4th of 7x squared plus 1. Since we only have one function of x, we can use our u substitution. So let's let u equal 7x squared plus 1. Then du dx is going to be 14x. That means then that f as a function of u is now cosine to the 4th of u. So df du is going to be 4 cosine cubed of u times the derivative with respect to u of cosine u. So even though we're doing u substitution, we still have a chain rule. So that means that df du is going to be 4 cosine cubed u times a negative sine u. So if we put it in a slightly easier order to read would be -4 sine u cosine cubed u. So now when we want to find df dx, we will find df du times du dx. And df du is our -4 sine u cosine cubed u, and du dx is our 14x. So we end up with a -64 sine of 7x squared plus 1 cosine cubed of 7x squared plus 1. Oh, and I forgot my x, 64x. There we go. So -64x sine, here, well, I'll make it a little bit easier for you to see here. It will be -64x. There we go. Sine 7x squared plus 1 times cosine cubed 7x squared plus 1. The other way you could think about this one is if you don't like the idea of u substitution on just the cosine to the fourth of u, you could do another substitution. You could say if u is the inside, it's the 7x squared plus 1, then you could make v the cosine of u. So there's a whole host of ways we could rewrite this problem. If we wanted to cast it in that light, we could say if we let u equal 7x squared plus 1, du dx is still 14x. We could say then let v equal the cosine of u. Then dv du is negative sine u. So in the end, we would have f is a function of v. It would be v to the fourth. And we would know that df dv is 4v cubed. And you're going, how does this relate to the chain rule and why is it so complicated? Because dx then would be df dv, got to clear the v, so we need a dv du, got to clear the u, so it's a du dx. It is a very drawn out way of finding the exact same derivative. So we end up with df dv is 4v cubed times dv du is negative sine u, and du dx is 14x. Start plugging everything in, you get 4 cosine cubed of u times the negative sine of u times 14x. So we end up with a negative 64x. Well, that would be the sine of 7x squared plus 1 times cosine cubed of 7x squared plus 1. So we end up in exactly the same place. It just takes us a little longer to get there. But it's completely possible to extend your substitutions and your chain rule out by multiple variables. So for H, I'm actually going to make this one a homework problem that I'm going to put into a Blackboard quiz, where I'm going to have you solve this one. It's very similar to the last one. So I'm going to have you solve this one to find the derivative of p with respect to x. So for this one, I'm going to say C Blackboard. For our, it's kind of like a homework / online quiz type thing, which I will put into our homework grade. So this will be a homework grade. So look for this problem and probably a couple of others. And I'm not going to have you type in the answers. I'm going to have you figure out which answers are the right one. I'm going to make it something that's pretty straightforward for you to. For our last page, we're going to look at an application of our chain rule in terms of physics. First, that's going to be our first application here. So the position of a particle along a coordinate axis is given at any time t by S of t equals cosine of 3t plus sine of 2t. What is the velocity of the particle at time t equals pi over 6? So remember, velocity is equal to the derivative of the position. So for this problem, we would look at our cosine of 3t would be the derivative of cosine is negative sine of 3t times the derivative with respect to t of 3t, plus the derivative of sine is cosine of 2t times the derivative of 2t. So we end up with a negative 3 sine 3t plus a 2 cosine 2t. And what we want to know then is what is v of pi over 6. And remember when I said we were going to keep practicing our reference angles? This is why. We need to plug it in and figure it out, because we end up with negative 3 sine of 3 times pi over 6 plus 2 times the cosine of 2 times pi over 6. So we simplify this to negative 3 sine of pi over 2 plus 2 times the cosine of pi over 3. Well, the sine of pi over 2 is 1, so we get negative 3 times 1, and 2 times the cosine of pi over 3. If you forget which one that one is, think of it this way. You've got pi over 6, and you have pi over 3. So pi over 6 is the smaller one, pi over 3 is the larger one. And remember, this one, pi over 6, has a longer cosine and a shorter sine. So cosine is greater than sine. The way that it works for pi over 3 is the exact opposite. So this is for pi over 3. You have your sine is greater than your cosine. And remember, these are both 1/2 and root 3 over 2. And we know that root 3 over 2 is greater than 1/2. So here, when we're looking at the cosine of pi over 3, that means that the cosine must be 1/2. So whatever it takes for you to remember, that's what we need to remember from our reference angles. We need to remember their cosine and their sine. So we end up with negative 3 plus 1, or just negative 2. The next two examples are very, very much related, and they're missing slight details. It should be f prime of 4 and f prime of 3. I'm going to do one of these with you, and I'm going to leave the other one, again, for homework on Blackboard. So we'll do B together, and I'll leave C as homework on Blackboard. So if we have h of x is the composite function f of g of x, and if g of 1 is 4, g prime of 1 is 3, and f prime of 4 is 7, then we need to find h prime of 1. So here we have h of x is equal to f of g of x, or if we wrote it out this way, f of g of x. And we know then that from our chain rule that h of prime of x is going to be f prime of g of x times g prime of x. So if we wanted to find h prime of 1, we find f prime of g of 1 times g prime of 1. So we just plug in these values. F prime of, well, g of 1 is 4, and g prime of 1 is 3. F prime of 4 is 7, so we get 7 times 3, or 21. And I'm going to leave part C as homework/quiz on Blackboard. It's an online homework/quiz. It's going to be labeled as a quiz or a test or something because it's the only way I can manage it on Blackboard, okay? So that is the end of our chain rule video, and the problems in the textbook are included in the notes for you to practice on your own, and they should help quite a lot with our web work for this week, which I believe is web work 6. So you should find that the video helps a lot with that. And then on Friday in class, we will go over the derivatives of both exponential and logarithmic functions.